Hey guys, what's up? I'm Mohit K. Kashyap, studying in Shri Venkateswara College of Engineering, Bangalore. I'm currently pursuing my BTech in Electronics and Communication. Today we are going to learn about the properties of Fourier transform. As we have all learned Fourier transform in our second year in M4 and M3. Now we are again discussing this topic in digital communications in 6th sem. So moving on to our next slide. So, well, there are several properties of Fourier transform. Today we are going to discuss about linearity, time shift, frequency shift, time and frequency scaling, time and frequency reflection. So, let's discuss about the first property, linearity. As you can see on the screen that for the first topic, the formula is a1 x1 of t plus a2 x2 of t. It gives a1 for this sign symbol is for Fourier transform. This symbol right here is for used for Fourier transform. Fourier transformed into a1 x1 of omega plus a2 x2 of omega. So let me preview this property in the next slide. So statement of this property is the linearity property of Fourier transform states that the Fourier transform of weighted sum of two signals is equal to the weighted sum of their individual Fourier transforms. So let's start with the proof now. If let's take x of t, if x of t and the Fourier transform of x of t is x of omega and y of t, and Fourier transform of y of t is y of omega, then z of t is equal to a into x of t plus b into y of t. Then we take the Fourier transform of z of t. What we get is z of omega is equal to a into x of omega plus b into y of omega. So what changed here? The only thing changing here is x of t and b of y of t into x of omega and y of omega. The two constants a and b are not going through any Fourier transform. They remain as constant as they are the constants. Meaning the Fourier transform of linear combination of signals is equal to linear combination of their Fourier transforms. So moving on to our next slide. Now moving on to our second property, time shifting property of Fourier transform. So let me read out the statement to you guys. The time shifting property of Fourier transform states that if a signal x of t is shifted by 2 in a time domain, then the frequency spectrum is modified by a linear phase shift of slope minus omega t naught. Therefore, if x of t, if the Fourier transform of x of t is equal to x of omega, then Fourier transform of then y of t is equal to x of t minus t naught. Fourier transform is equal to y of omega is equal to e power minus j omega t naught into x of omega. So what they are saying is the time shift in time domain, which is the t minus t naught, is equal to frequency shift in frequency domain. So if you minus or add t naught in the time domain, which results in the exponential form of e power j omega t naught into x of omega, meaning a shift of t naught in time domain is equivalent to introducing a phase shift of minus omega t naught, but amplitude remains the same. What they're trying to tell is there is no change in the amplitude. The amplitude remains the same, but the time shift of the exponential part e power minus j omega, that changes. So moving on to our next slide. So moving on to our next property, what we have here is frequency shifting property. So the time shifting property identifies the fact that a linear displacement in time corresponds to linear phase factor in frequency domain. This becomes useful and important when we discuss filtering and the effects of phase characteristics of a filter in the time domain. Proof: if x of t, if the Fourier transform of x of t is x of omega, then y of t is equal to x of t minus t naught. The Fourier transform of this equation is y of omega is equal to e power minus j omega t naught into x of omega, which means a shift of t naught in time domain is equivalent to introducing a shift of e power j minus t naught into amplitude remains, and amplitude remains the same. There is no change in the amplitude, guys, even here. Actually frequency shift property and time shift property are a bit like vice versa thing, okay? LHS and RHS, which is like vice versa thing. Moving on to our next slide. So guys, our next property is time scaling property of Fourier transform. So let me read out the statement to you guys. The time scaling property of Fourier transform states that if a signal is expanded in time by a quantity A, then its Fourier transform is compressed in frequency by the same amount. Therefore, if the Fourier transform of x of t is ft x of omega, then according to the same time scaling property of Fourier transform, x of at gives ft1 by mod of a into x of omega a. So there are two conditions for this. When a is greater than 1, then x of at is compressed version of x of t, and when a is lesser than 1, the function x of at is expanded version of x of t. So let me prove you this point. By definition of Fourier transform, we have f into x of t, Fourier transform of x of t is equal to x of omega is equal to, what we have is integration minus infinity to infinity x of t into e power minus j omega t dt. Then what we have is f of x, for a transform of x of at, which gives us integration of minus infinity to infinity x of at into e power minus j omega t dt. So as we can see that there's no change in the exponential factor. The only thing changing is x t t and at over here. Okay, moving on to our next slide. Putting at equals u, then t equals ua and dt equals dua. Fourier transform of x of t is equal to integration of minus infinity to infinity x of u into e power minus j omega of ua into dua. So further expanding this equation, Fourier transform of x of t is equal to, we get the a outside, a into, as a is a constant, a into integration of minus infinity to infinity x of u into e power minus j omega a u du. So we are having two cases over here. Case 1, when a is greater than 0, then what happens is Fourier transform of x of at becomes is equal to 1 into a divided by 1 divided by a into integration of minus infinity to infinity x of u into e power minus j omega a u du, which further gives 1 divided by a into x of omega a. Case 2, when a is lesser than 0, then Fourier transform of x of at is equal to minus 1 divided by a into integration of minus infinity to infinity x of u into e power j omega a u du. And the last equation is f of x into at is equal to minus 1 by a into integration of minus infinity to infinity x of u into e power minus j omega a u du is equal to minus 1 by a into x of minus a x of minus omega a. Moving on to our last and final slide. What we were concluding here is f of Fourier transform of x of at is equal to 1 by mod a into 8 into x of omega a, or it can also be represented as x of at is equal to Fourier transform of ft1 divided by omega mod a into x of omega a. So this is it, guys. Thanks for watching my video. I hope you like it. If you don't like it, I don't care. So bye, guys. Take care. Have a nice day.